Okay, the time is 9:30, so let's begin here. So for today, you need to examine the notes and the corresponding videos for Section 2 in terms of subsections 1 and 2 and part of subsection 3. And so usually what I do at the very beginning of a course in this kind of a format is I do a brief review of the corresponding material. And the purpose here is to show you what I think is most important. So think about this then eventually when you get to studying for tests. Also, this might, by me going through this review here, this might prompt you to some questions that you might want to ask. Okay. So in subsection 1, it was just simply, well, let's take a look at the type of example data that we're going to be looking at in this course. We had the OSU enrollment example, we had the S&P 500 example, S&P 500 index example, and then also the classic sunspots example. And so what this section looked at is, okay, how can we visually display the data? And also, what kinds of questions will we be trying to answer with respect to this kind of a data? What are the things that we're going to be looking at with respect to this kind of data? And so plotting is really not too difficult. The main thing to think about is that, there's two main ways to use the plot function. You can use it just with the x argument. And so what's in the x argument then goes on the y-axis of your plot. And then R plots that against simply an index, which will typically be for us time equal 1, 2, all the way up to, let's say, n, if we have n points. And then the other way to plot the data is probably what you're used to doing. What you put in the x argument goes on the x-axis. What you put in the y argument goes on the y-axis. What can make it a little bit more tricky to work with is that when you have dates. And so I introduced the as.date function that can be very useful and gives you a number of different formats to work with for dates. Now, once you plot then the data, then you're interested in understanding, well, what kinds of patterns do we see there? What kinds of dependence do you see in that data? And then lastly, and this is more so getting into the future, well, how can we forecast? Okay, because if you see certain patterns, if you see certain kinds of dependence, that might lead you to think about, okay, for time, let's say n plus 1 or n plus 2, what that next value could be. Then in subsection 2, we looked at some very basic models in terms of notation. Sorry for those of you who are hardcore in terms of statistical theory. We do use lowercase letters for our random variables. It's just kind of a standard that you will see in time series analysis. We don't use uppercase letters. Then we looked at two different, then we talked about white noise. And all that white noise is a fancy name for what we normally think of in statistics as independent observations. Just in our case, these observations are taken over time. These white noise observations, this white noise also means that everything has the same distribution too. So IID, independent and identically distributed. Then we looked at two different components to time series models. We have a moving average, which says basically if you have a 3-point moving average, let's average over these 3 points at a time. Then we also had autoregressive models, which basically puts in the context of what you've seen elsewhere in terms of a regression model. Now in terms of time series analysis, where we use, let's say, the past observation to predict the present observation. And then lastly, we talked a little bit about, in the notes, data simulation. Maybe more so in this class than in any other statistics course you'll have. Data simulation plays a role for you to help you understand the corresponding material, what these models actually mean. And then lastly, subsection 3, that was over dependence, where we actually derived our first autocovariance function. So all of you have seen covariance in another context before, where you have two random variables, let's say x and y. Find the covariance of it. Measures the dependence. Positive covariance or a covariance value that's greater than 0 means you have positive dependence, meaning as x goes up, y goes up. As x goes down, y goes down. Negative means the opposite. Now we have autocovariance because that auto comes into play because we're looking at, let's say, time point t versus time point t minus 1 for x. It's the same variable, but just at different time points. And we're looking at the association between them. We will be deriving these autocovariance functions a lot, especially for the first half of the course. And then also in the notes, there was a discussion about lat. This is a common term that we will use and just helps you to say how far apart is one time point x for x versus another time point for x. So if I have x sub t versus x of t minus 2, the lag is 2. If I have x of t and x of t plus 2, the lag is 2 as well. Okay? That's a really brief review. Are there any questions over the corresponding material? Okay. So there's a number of announcements, reminders, and other items that I want to get to or get through before we start talking about project number 1. First of all, just in terms of how I do this course, when I do blended learning, I will always start off with a Word document such as this at the very beginning of class. A lot of the material in here is like reminders for what I want to discuss, but there will also be parts of examples and maybe test reviews and stuff like this in this document. This document, generally speaking, I do not make available on my course website. The main reason is because I want you to take notes in our class. Now, if there's ever a time where you're taking notes and you don't quite get written down what you needed to get written down, of course, remember I'm recording all these classes, and so you can always go back to the recording to get what you maybe miss. Also, I don't post this typically to my course website because I want you to pay attention during class too. Now, week number 1 quiz. Everyone got 5 points unless you heard from me otherwise. The points are listed in the grades portion of Canvas. Now, one of the most important questions that I asked on this particular quiz was, could you take the test early? Could you take it late? And everyone said yes. Okay, so once we get closer to the test time, I'll let you know exactly, is it early, is it late, or is it maybe a combination of both? I am still uncertain if there's actually a class in here after us. So that's why I can't say for sure at this time exactly what we'll be doing. The quiz for week number 2. So this is just a reminder that every Tuesday during the semester, you will have a quiz that will be due at 8 p.m. I was taking a look at how many students had done the quiz already, and looks like I think it was about 8 already have, so that's good, 8 out of 12. But don't forget that you need to do it. Don't forget that you need to hit the submit button to actually submit it to me. Otherwise, I don't know that you've actually completed it. Once all the quizzes are turned in, or we get to 8 o'clock, I will take a look at the quizzes, and I will then have the grades posted, and you will receive an automated email from Canvas when those grades are posted. I typically will not go over these quizzes in class unless there's some kind of question regarding them. Now, after I see the quizzes, if I see, let's say, a commonly missed question on those quizzes, I might post something to the discussion board about it or talk about it in the subsequent Tuesday class. This Thursday, you have this group membership quiz as well. It's very easy, so don't worry about having all these quizzes so quickly at the beginning of the semester. About half of you have already completed it, so that's good. It is due at 8 p.m. on Thursday, if you can, submit it actually sooner. Because especially if you do not have a group already, this gives me time to help you find a group and so that you can get started on this project sooner. And very lastly, then, not a big deal, but the sunspots data that was in subsection 1. When I was going through the notes, I noticed that the link there doesn't work anymore. So if you are really, really into sunspots and you click on that link and you want to learn more about that, here's an alternative place that you can go to get that same data. There's also other information they have there as well for sunspots data. Okay. Let's next talk about project number 1. This is due February 15th at 8 p.m. Get it to me by then. I do not accept late projects. And I mentioned this last time. It's available on the graded webpage. Hopefully you've taken at least a quick look through it before our class. This project is over section 2. So there are parts of this project that you do not have enough background yet to do. And that's okay. We will obviously continue going through the material before February 15th so that you do have all the background for it. For this project, you can work in groups of up to 3 people, or you are required to work in groups of up to 3 people. And I kind of said this last time, why do I have group work for these projects? And the reason is because you can learn not just from me, but also your fellow group members. And I know as a student, I benefited a lot from group work. I think students in my courses have benefited a lot from it. But there are cases where group work is not done as it should be. So let me give you an example of the way not to do group work. Let's say the group of 3. One person chooses to do problem number 1. Another person chooses to do problem number 2. And the last person, that poor person, has to do problem number 3 and 4 on that project. Okay? Then maybe an hour before the project is due, you just simply merge your files together for what you've completed, each of you separately. You haven't talked about it at all. And then you just turn in that. That's it. That is not how to do group work. You do not have the benefits of talking to your classmates about how to do the particular problems. Instead, here are 2 alternatives for how to do group work that is how you can get benefits from it. One way is to, similar to what I just said before, is each person does essentially a problem themselves, and they do it separately. And they do it separately from the other people in the group. But you schedule a time, maybe a couple of days before the project is due, where you all get together, and then you talk about how to do each of the problems. So maybe the person who does problem number 1 kind of leads a discussion through, this is how I approach problem number 1. And then you can all decide, well, do we agree with that answer? Should we make changes to it? And so on. And maybe the person who does problem number 2 leads the discussion for problem number 2. And so the key is that you finalize answers then for the group as a whole, and then that's what you turn in. That's one way to do it. A second way to do it, maybe it's a little bit better, is that everyone does the project on their own separately, the whole project itself. Then, a couple of days before the project is due, you schedule a time where you all get together and you go through each part of the project step by step, and then come together to come up with a final answer. Okay. I assume that you probably have all knew this before, but sometimes it's helpful for a little bit of a reminder as well. Okay. So please choose the right way, not the wrong way to do group work. A key is that all group members need to understand the answers submitted. Okay. So what I have here then is for problems 1, 2, 3, and 4, what the corresponding sections are for these particular problems. And so we're going to begin by talking about problem number 1, subsections 1 and 5. So you can do the 1 part now. The 5 you're not going to be able to do until you cover the corresponding material in the course notes. So let's take a look at problem number 1. So one thing that I do to prepare for teaching a course is the weeks leading up to it, I look for, let's say, new, interesting data sets that I can use for like projects like this. And I think I ended up coming across about 7 or 8 different data sets for this semester. But for these projects, primarily, we're just going to focus on 2 of them. Maybe you'll see some of the other data sets I came across on tests. But this first data set is one dealing with earthquakes that are, let's say, of a significant magnitude. And it's a fairly small data set, and I like to give small data sets at first because it just helps with, it's easier to work with a smaller data set when you're learning the material than necessarily, a large data set. And so this data set gives me by year, starting with the year 2000, the number of earthquakes that occurred. And so we had 1,505 in 2000, 1,361 in 2001. And what motivated me to choose this particular data set is that, I would think that seismic activity might be related from one year to the next. I would think that. I'm not an expert on earthquakes, but it seemed logical to me because I also was thinking about, if you ever hear in the news media, they talk about there are 10 forecasted hurricanes in the Atlantic Ocean expected this year. How do they come up with that? Well, I bet they use some kind of time series analysis for it. And I thought, I never hear anybody say there are 10 earthquakes that are expected, next year. But I would think that there would be some kind of dependence because you would think, okay, if there's a lot of activity last year, maybe there might be a lot next year, or in terms of seismic activity. Or alternatively, let's say if there's a lot of earthquakes one year, well, maybe the Earth's crust has now done enough moving that we're going to come to a dead period and that we won't have as much. And so I thought this was just kind of a simple data set to investigate that further. So through projects 1 through 4, you will be actually investigating this data set. Okay. So the data, as I was just showing you, is in actually a comma delimited file that you can download from the grades webpage on my course website. And this first part, very simple. 1A, read in the data and show me that you've read in the data correctly. It's only worth 1 point because it's so simple. But let's actually do this problem in class so that you can see what I expect for you to turn in. So probably the easiest way to complete these projects is simply download the Word file. Then as I just did here, insert a space between, let's say, A and B, and this is where you put your answer. Okay? So we need to read in the data. So I've already downloaded the data set to my computer. Let me make this a little bit bigger. Okay. Is this code big enough so that everyone can see it? If not, I can blow it up more. Okay. So I've downloaded the data. I know a particular folder where I downloaded the data to. It's actually located, this is my folder structure right there. And there's a number of different ways that you can read in data. Probably the most common is simply just to use the read.csv function. And so what I do here is I use a function called setWD, which stands for set working directory. I always set my working directory because I often will be working with multiple files and different folders on my computer at exactly the same time. So it's very helpful to set the working directory, despite what some other people say about that you shouldn't. And so this tells R, hey, this is where my stuff's located. And I use simply the read.csv function. I specify my file name, earthquakes.csv. I put it into an object called set1 for the lack of a better name. And then I use the head function with all the defaults that will print off the first 6 observations. Okay, so now that I have that, what I'm going to do is copy this into my Word file and then paste it there. Just because of a quirk with TIN-R that I use to do my stuff in R, extra spaces are inserted. And so there's my answer, partially. Now, although it's not a big deal on this particular problem, typically the way that we show our code and output, or actually even when you work with other languages too, is typically you use some kind of like courier-like font. In other words, some kind of font that has each letter the exact same width. This is helpful because often when you do programming, you indent stuff to help you understand, well, maybe this is this is a subset of something else. And so what I want you to do is reformat this code here so it looks like what you see in my course notes. And I've set something up for you to make it easy. Notice how I have all this highlighted here. I can use a word style that I have in my project document called R10, which transforms it to Courier size 10 font. It will also indent stuff mostly properly from what you need. And so for this particular problem, this is all that you need to do to get full credit for it. Now, there will be other problems where you might have to, let's say, explain your answer or maybe do some other stuff. And this is where you can type your additional answers afterwards. When you type it up, please make sure that you use proper English. You're using nice periods and commas when needed. You are spelling stuff correctly. Make sure you have your spell checker on. And this is what your answer should look like, something like this. Are there any questions? Okay. Now, this is the way I think most students in my courses typically, will do their projects, but there are alternatives. Okay. Where is that? There we go. If you want to hand in a PDF document rather than a Word document, so you can do the stuff in Word, hand in the Word document to me, or you can just somehow use some other language or other software package and hand in a PDF. That's fine. I have a tablet PC here, or actually a Surface Pro, and I can use my pen to grade as necessary. I use the track changes tools and various software packages to indicate my grading comments as well. Something that if you have not had any experience with that I do recommend that you try to do, and usually some students will do their projects like this, is use a dynamic document generation tool to do your projects in. What that basically means is that you can, let's say, combine your R code and your normal type text into one document. You press a button essentially on your software package and everything is merged together, including the R code as it is run. So many of you have experience with, for example, R Markdown. That will be another way that you could do this project. Just make sure that you have everything properly labeled as 1A, 1B, 1C, and so on. My favorite way of doing this stuff is to use the knitter package in R, where it allows you to combine let's say your LaTeX or your LIX stuff together into one document. You press a button, and all the R code and output is then inserted into a PDF with your normal type text. If you don't have any experience with this, if you don't have any experience with that, that's completely fine. You don't have to do that. If you do want more information about how to use the knitter package, if you go to my Stat 850 website, I do have information. Another way to do this is in Word itself. You could actually put your R code in there, press a button, and the R output will be automatically inserted as well. There is an add-on to Word called Stat Tag that I believe is still free. Some people at Northwestern developed it about 7 or 8 years ago. And that will be another way to do this. Okay. For those of you who have taken Stat 850, do you still talk about R Markdown in that course? Yes. Okay. Have you talked about Quarto yet? I see maybe one. Okay. So that's a fairly new way to do some of this stuff. Again, put together by the people of RStudio that has some similarities. I have not used it yet. If you end up using Quarto, let me know. I would love to see your I guess the document that was used to create your Word or PDF output. Okay, so let's go back to the project. So let's talk about part B here. So we have this earthquakes data. Do a plot of the earthquakes data very similar to what you saw in subsection 1. On the x-axis, I want the years to be actually represented rather than, let's say, t equal 1, 2, 3, and so on. So please put the years there. Make sure you properly label axes and stuff, and then describe any trends that you see in the data. So for this particular problem, what you turn in is that you're going to have some R code and output. You're going to have to insert the corresponding plot, and then you're going to need to then give an additional description of the trends that you see in the data. Okay? That's what I would expect to see there. Now, parts C, D, and E rely on subsection 5 of the notes. So in our next Tuesday class, we'll talk about this a little bit more. Okay, let's talk about problem number 2. So, So if you see my website, which I'm sure you have by now, you know that I have a lot of different parts to it. And over the years, I have always had some kind of website trackers on it, because I want to know who's using my website, how much they're using it, and stuff like that. So there's various, there's Google Analytics tools that you can use. I actually use something else myself. And so, like, for example, for the last 24 years, I've kept track of the number of visits that I've had to my chrisbuilder.com webpage. So I have a long time series of data. And I've always wanted to take the time to actually analyze it. And this semester I said, okay, let's do that. And I decided, though, not to use chrisbuilder.com, or I almost did like our course website itself, so you can see what happens during a semester for a course in terms of student usage, essentially. Instead, though, I decided to use this data that's, I guess, motivated from the COVID-19 pandemic. So one of my previous PhD students, her name is Brianna Hitt. She's now an assistant professor at the Air Force Academy. And as part of her dissertation, she put together a Shiny app. Does anyone know what Shiny apps are? Probably some of you do. Okay. What Shiny apps are is basically a way to have to allow users to use basically a web interface to use R, essentially, where the person who's using the web interface doesn't really know that typically the R is in the background that's doing this stuff. And so I pay a few $100s per year to RStudio to host a few different Shiny apps on their web server. And my student put together a Shiny app that looked at some of the stuff that she was working on for her dissertation. She did her work in what's called pool testing, also known as group testing. And what we wanted to do was to put together a user-friendly app that people in laboratories who would use this statistical method, that they could go to, do some calculations without necessarily knowing that they're using R. Because it would be difficult for them to program in R. And so, without going into all the details behind it, the basic idea is that if you use this group testing or pool testing method, you can dramatically reduce the number of tests that you need to test for an infectious disease. And we had developed this app for people who were actually testing for sexually transmitted diseases. We released it in February 2020, and then in March 2020, then at least in the US, that's when the COVID-19 pandemic really hit. And we started noticing that a lot of people that we weren't expecting were using this app. And so because of that, I said, well, I'm going to put a tracker on it so that I know who's using it and who's not. And we're almost to the data. But here's for the first 6 months that I was tracking stuff with this app. This is the locations around the world for people who are using this. And so you can see it was primarily people in laboratories were finding this to be quite useful to use this app. And one reason why I put this up there is that all of you, or at least most of you, will be doing some kind of research in the future. And you can see you can have this kind of a worldwide effect too with your own research. And we just had a way to track it. Okay, so the part of the data that I will be using in this class is what's shown here. Let me make this a little bit bigger. And so I started tracking who was using this app on March 27th of 2020. And simply what we have here is a series of data collected over time for the number of visits to this app that we have on the web. So for March 27th, 12 people used it, or essentially there was 12, let's say, hits on the website. March 28th, there was 1. And this is done for an entire year. So you can see, keep on going down. Eventually, we'll get to 365 days. Okay? And so what we're going to be looking at least in this project, I hope for another project as well, I want to understand the dependence that we have in this data over time. Excuse me. And so let's talk about how we can do that. Oops. So part A, simply read in the data. Do like what we just did with the earthquakes problem. Part B, plot the data over time, where in this particular case, I want you simply just to use an index of time, 1, 2, 3, all the way up to 365, on the x-axis. Describe any trends that you have in the data, that you see in the data. Now for part C, construct the plot in B again, but use now the actual date. So this will give you some experience of how to work with dates. Again, in the file itself, we can see that indeed there is a column that has the actual date. Then part D here, construct the same plot again as in B, but use separate lines that connect the points for each day of the week. So with the OSU enrollment example, we had fall, spring, and summer enrollments, semester enrollments. And then we broke the data up by semester, and you could see, oh, there was some interesting things that were happening. And maybe since the data wasn't too big, you kind of saw that by the oscillating patterns throughout the time series, the original time series plot. But by breaking it up by the semester, it really helped you see that. And so for this particular plot, I want you to do the same thing, but break it up by the day of the week. What do you think might happen? So this is not a rhetorical question. What do you think might happen if you break it up by day of the week? A spike on Monday. Yeah. What about Saturday and Sunday? A lot of these labs were working 24 hours a day, 7 days a week. But normally we would expect, okay, people aren't going to be there in those times. And I just went back up here a second here. I apologize if I didn't explain this very well to begin with. So this Shiny app was used by laboratories that were testing for COVID-19. And they were looking for ways to test more efficiently so that they could test more specimens than what they were if they were simply doing their normal way of testing. And so that's why they were using the Shiny app to try to figure out how best they could use this group testing method. So if that wasn't clear beforehand, I apologize. Okay. So now whenever you're doing a plot like this, when you're breaking stuff up, we need to make sure we can distinguish, well, is this Monday? Is this Tuesday? Is this Wednesday? So make sure you use like different symbols for your plots for the different days of the week. You're using different colors so that we can distinguish what's going on. Now, in these kinds of settings, where, I think generally speaking, we would expect some kind of trend based upon the day of the week. This is often referred to as a seasonal time series. It doesn't really make sense to call this seasonal here because we have just simply days of the week. But that's the general term that's used. Even with the OSU enrollment data, people will often refer to that as a seasonal time series because what's happening in the fall is going to be different from what's happening in spring. It's going to be happening different in the summer. And because of that, you would expect maybe the dependent structure to be different from what you would normally think in terms of, let's say, time 10 affects time 11, which affects time 12. Instead, maybe time 10 affects time 13, which affects time 16, which affects time 19. That's called a seasonal pattern or seasonal dependence. And so by doing a plot like this, it helps us distinguish if that actually occurs. Otherwise, it might be a little bit difficult to see that if I'm just simply plotting everything from t equal 1, 2, 3, 4, 5 and connecting all the dots with lines across those consecutive time points. Okay. Now, part E and G depend upon subsection 5. So I'm not going to go over that here. Let's see. So problem number 3, then in the project, deals with subsection 6. So the very last part of section 2. And then problem number 4 deals with subsections 3 and 4. And you can get a start on that now I'm going to just briefly talk about part of it. So consider the following, let's say, model that we have here, where x of t comes about through the product of two white noise terms, one at time t, one at time t minus 2, plus then a white noise term at time t minus 1. So with that, well, I want you to actually derive the expected value of x of t. So when you do the derivation, I want you to actually type it out formally. So you would say, well, I'm not typing it out because it's just easier for me to use a pen with teaching. Expected value of x of t is equal to the expected value of wt times wt minus 2 plus wt minus 1 is equal to, and then you do the next step of the short proof. Show me the steps. Don't just immediately get to one answer after that. Show me the steps. This is for your benefit to do that, because if you mess up along the way, I have a way to assign you partial credit. So that's why I expect you to see the steps. Part B, what is the autocovariance function for this particular scenario? So, we have gamma of, let's say, I think I always use S first. So gamma of S of t, well, what is that? Well, that's the expected value of x sub s, xt minus expected value of xs, expected value of xt, and then you keep on going down and doing the proof. There was an example in the notes of the process that I used. Now, in order to get the autocovariance function, of course, you might have to consider, well, what if s is equal to t? What if s is equal to t plus 1? What if s is equal to t minus 1? And so on. So there's going to be a number of different cases that you're going to need to see. Eventually, you're not going to have to go to t plus 20. You're going to see a pattern that occurs. And once you see the pattern, just state what you see. And then in the end, state the autocovariance function like what you saw in the notes. This part C then depends upon subsection 4. Now, when you do this problem, I do expect you to type it out. You probably will need to use an equation editor in Word or whatever software package that you're using. Do not write out your answer, take a picture of it, and insert it in the document. Why? Well, at some point you will need to write out equations formally, so that's why I want you to do this. Also, don't use stuff like this. Where you use a text-based equivalent to a mathematical symbol, don't do that. Actually use the correct mathematical symbol. Don't do like x underscore t, where if you're using LaTeX, that would mean x subscript t. Don't do that. I want to actually see the proper subscript in there. So don't use the text-based equivalent. Let's see here. So lastly then, how do you turn in the document to me? Simply have one of your group members email it to me with all the other group members copied on the email. What I will do is once I get that email, I will reply with simply like a thank you. And that's your way of knowing, hey, I did get it. If you don't hear back from me like within a day or something, you might want to check with me because maybe somehow it got lost in the mail or I hate to say this, sometimes it might go to my junk mail. Not saying that what you send me is junk, but obviously it could happen. So if you don't hear from me within a reasonable time period, please make sure you contact me and to double check on if I received it. For the file that you turn in to me, please make the file name the last names of all the group members. Just as helpful for me for organization purposes. also put the names of all your group members, of course, inside the document itself. I will then grade these documents. Do note that once you turn it in to me, I might start grading it immediately. So if you find out a few hours later, like, oh, I should have answered a problem a different way, it might be too late to change your answer. So I might grade as soon as you turn it in to me. I just like to get ahead of things, so I will frequently start grading these before the actual due date and time if I have some that are already turned in. Once I grade these documents, then I will email them back to the group members. I'll do a reply to all to your email. I will also post a full answer key to my course website. Okay, so that's a lot of talking there. Are there any questions? Okay. So there's just a few other small things that are related to this class that I just want to briefly talk about because we do have time. The first one. This deals with the format that we're using for this course. I have sometimes had students tell me that they think a blended learning format leads to students having to do more work. They have to spend more time on the course. And there's different definitions of what time means in terms of spending on a course. But here's one that we could use. And that is, what would be the normal amount of time that you would spend with a regular course format? And I think I briefly talked about this a little bit last Tuesday. And the amount of time would be 15 weeks at 2.5 hours per week. So that would be 37.5 hours. I look at that number as then my goal for this blended learning format for what we get to with respect to the number of hours that I have of recorded videos, the amount of time that we spend here in this Tuesday class, the amount of time that you'll have for Thursday tests. I guess obviously our first Tuesday class as well is counted in there. And so there's approximately about 20 hours of videos that I've recorded. And if you combine the tests and a variety of different other things here, these Tuesday classes, if we were to average for the rest of the semester, approximately 30 minutes, or if we would spend about, on average, 60 minutes per these Tuesday classes, what would happen? So here's for 30 minutes. Here's for 60 minutes in terms of the total number of time that that you would have work time for the course. And you can see if we are averaging about 60 minutes, or right about the 37 and a half. And so if we use the amount of, let's say, class time, equating it to videos and stuff like that, if we use that as a metric for how much work is there for a class, it all evens out. I purposely, again, watch this time during the semester because if we are hitting 40, I know that's too much and I don't want to overload you. If we're at like 32, I know, okay, well, I'll look to see if I can add some stuff to our Tuesday classes. And then lastly here, in time series analysis, and you'll notice this if you look at our book or other books, there are two different ways to think about time series analysis. They're referred to as the time domain and the frequency domain for how to do time series analysis. We will focus in this course on the time domain, where we will try to find, let's say, equations like this. So we have x at time t. So this could be, for example, the number of earthquakes at time t. We're going to equate that to what happened at time t minus 1 times a parameter that we will want to estimate, plus a white noise term at time t, plus another white noise term, but now in the past at time t minus 1, times a parameter that we will want to estimate. Those are the kinds of models that we will be looking at in this course. This is what you do for a time domain analysis. Now, in terms of the frequency domain, basically, you equate x of t to a combination of cosine and sine terms. That's one way to go about doing it. You might be wondering, well, why? Well, if you remember seeing some of the plots in the first set of notes for today, you saw kind of oscillating patterns that were occurring there. And maybe you could think of some kind of combination of cosine and sine waves, that's what you saw in a trigonometry class, could be potentially used to help understand what x of t is. That's called the frequency domain. Chapter 4 of our book discusses it. The time domain is much, much more widely used. And so a common time series analysis course will spend, let's say, 3/4 of the time on the time domain, and then they'll go back and look at exactly the same kinds of purposes, or they'll have the exact same kinds of data sets, try to do exact same kinds of analyses, now in the frequency domain for the last 1/4, or the other 1/4 of the course. I don't like that approach. Instead, I stick just with the time domain when I teach this because it allows us to do more stuff, more unique stuff, rather than redoing exactly the same things, but just from a different perspective. But if you are interested in the frequency domain, take a look at chapter 4 of Shumway and Sofer's book. Okay, so that's basically all I have here for today. Are there any questions before I end class with a discussion about what's next for our course? Okay. So today, again, you have that Canvas quiz that's due at 8 p.m. Thursday, we will again have our help class at 9:30. This would be an excellent time for you to get together with your group members in the classroom to discuss or to start project number 1. You're not required to do that. Again, these Thursday classes are optional, but that could be a great time for you to start organizing what you're going to do for your project, especially if you already know your group members. The group member quiz is due at 8 p.m. on Thursday. If you can, get that done sooner rather than wait till then so that I can, if needed, form groups. The next Tuesday, we'll have our regular class. You need to, for next Tuesday, go through the course notes, go through the videos for the remaining part of subsection 3 and also subsections 4 and 5. 5 is now going to start getting into how we can estimate dependence. So we're going to look at basically something that's like a Pearson correlation coefficient, but now in a time series context. It's going to be called an autocorrelation. We're going to estimate that. For those of you who also want that additional resource in terms of where we are in the book, it's sections 1.3 and 1.5 of the book. There is a discussion of what's called a cross-correlation function that I skip in my notes. We will get to it later in the semester, though. We will continue discussing project number 1, and of course, you'll have another quiz due next Tuesday. Looking further ahead, project number 1 is due Thursday, February 15th at 8 p.m., and test number 1 is Thursday, March 21st. So that is all here for today.